They call me a comet. They call me a dragon. They have no words for my true form.
Aurelion Sol, League's own omnipotent being, also known as the Star Dragon. In lore, he stretches on for millions of miles with a mass larger than any other sentient being known to man, as he forges stars from the very palm of his hand. But those aren't the stars we'll be concerning today. Aurelion Sol is named the Star Dragon for a reason, but the term star itself is pretty vague. Stars come in all shapes and sizes, from white dwarfs to red supergiants, from our own sun to neutron stars billions of times denser. And density is a variable that allows us to relate these real-life objects, called stars, to Aurelion Sol himself, and determine what kind of Star Dragon is Aurelion Sol. Now, before we start, I want to acknowledge the variables and theories that we'll not be applying to this problem. Things such as friction, Earth's gravity, the curvature of space due to the overwhelming amount of mass in a small area, and, thanks to the insight of my buddy Sam, the three-body problem. These interfering factors make these calculations extraordinarily harder than they have to be for both parties. Additionally, we will only be looking at Aurelion Sol's stars without celestial expansion, his W, toggled on. This video is meant to be for fun and not necessarily 100% accurate, and more of an estimation, so these smaller changes in measurements caused by the before-mentioned factors do not serve that big of a purpose. Not to mention the fact that the three-body problem is literally rocket science. So, in this video, a perfectly spherical Aurelion Sol is being orbited by a single perfectly spherical star in a perfect universe without any external forces. That makes it a lot easier. So, to start, we will look at Aurelion Sol's star orbit and the Star Dragon's gravitational pull. In order to do so, we must find basic measurements of his stars and himself in his scaled down form in-game. This is slightly more difficult than you might think because in lore, Aurelion Sol is literally hundreds of millions of miles long, able to hold our own sun in the palm of his hand. More importantly, that means that there is not a single Reddit or boards post that lists Aurelion Sol's in-game height or length. So, similar to Warwick, we'll have to use another champion as a unit of measure until we can find the dimensions we need. Dealing with width, such as that of the stars, means that we need the width, not the height of another champion to measure from. However, heights were the only thing I could find, so I chose a very small, yet rectangular champion to measure height and width from, Amumu. His small height provides a more accurate unit of measure, and his rectangular body allows for a simple height to width ratio to calculate his width from his height. According to this Reddit post, Amumu's height is about 3 feet and 7 inches, which equates to about 1.0922 meters. After some measurements, it appears Amumu's width is about 5/8 or 62.5% of his height, meaning he has a width of about 0.683 meters. Now, if we look at Aurelion Sol's star width, it appears to be about 60% the width of Amumu, meaning that the stars have a width or diameter of 0.410 meters. Dividing the diameter by 2 yields a radius of 0.205 meters. From here, we can use the formula V equals 4/3 pi times the radius cubed to find its volume, since we're assuming it is a perfect sphere. Plugging in the numbers provides a volume of 0.036 meters cubed for Aurelion Sol's stars. From here, in order to find the mass of the star from its volume, we must know its density. Fortunately, similar stars have similar densities. So, if we want to find out the density of an average real-life star, say our sun, then we can use that density as the density of Aurelion Sol stars. Google reveals that the average density of the sun is about 1410 kilograms per meters cubed, which is about the same as the density of water. Anyways, by using the simple formula density equals mass over volume, we can calculate that the mass of one of Aurelion Sol's stars is about 50.76 kilograms. Now, the next step is to find the force needed to be exerted onto the stars to keep them in orbit around Aurelion Sol. To do so, we must first find the radius of the star's orbit. From there we can find its velocity and centripetal force, and thus the mass of Aurelion Sol. But first, it appears to take about 4 Mumu stacked side by side in order to go from the center of one of the stars to the center of Aurelion Sol himself, which means the radius of the orbit is about 4 times 0.683 or 2.732 meters. Next is the velocity. In order to use the formula velocity equals distance over time, we must find the distance, which in the case of a circular orbit is the circumference, and the time it takes for a star to make one revolution around Aurelion Sol, To find the circumference, we can use the formula c equals 2 times pi times the radius, or 2 pi times 2.732, which gives us a circumference of 17.166 meters. To find the time it takes for a star to make one revolution around Aurelion Sol, we can just simply use a stopwatch, which gives us a total star year of 5.18 seconds. Now, when plugged into the formula v equals d over t, we get a velocity of 3.314 meters per second. With this number, we can combine the formula's centripetal acceleration equals velocity squared over the radius, and centripetal force equals mass times centripetal acceleration, to get the formula F of c equals mv squared over r. Plugging in the numbers leaves us with a force of 204.054 newtons exerted onto a star in order to keep it in its current orbit. Finally, we need to use the formula that relates mass, orbit, and the forces between two bodies. So, we'll use the formula gravitational force is equal to the gravitational constant times mass 1 times mass 2 over the radius of orbit squared. If we rearrange the equation, we can see that by plugging in the variables of gravitational force, the radius of the orbit, the mass of the orbiting object, or in this case, the star, and the gravitational constant of 6.67408 times 10 to the negative 11 with these units, we can determine Aurelion Sol's mass, which turns out to be 4.497 times 10 to the 11 kilograms, or 449 quadrillion kilograms. Yes, this is an extremely large mass when compared to other beings of similar size, like Garen, Azir, or even Vi with her gloves. But when compared to other celestial bodies out there, the Star Dragon doesn't seem that stellar. Our closest star, the Sun, has a mass of 1.989 times 10 to the 30 kilograms. The largest planet in our solar system, Jupiter, has a mass of 1.898 times 10 to the 27 kilograms. Earth's mass is about 5.972 times 10 to the 24 kilograms, and even the Moon's mass is 7.348 times 10 to the 22 kilograms, nearly 100 quadrillion times more than Aurelion Sol. But mass isn't necessarily the best way to compare Aurelion Sol and other bodies. A better variable to compare would be density. Average stars like our Sun have all around the same density, 1 gram per cubic centimeter, which provides a starting point on a scale where we can place Aurelion Sol. So, by finding the density of Aurelion Sol, we'll be able to accurately gauge where on the spectrum of stars he falls onto, and thus what type of star category the Star Dragon falls into. Unfortunately, the only formula that relates mass and density is d equals m over v, which requires us to find the volume of Aurelion Sol, something that cannot be easily and accurately done. But, as I said previously, a lot of these calculations are approximated and for fun, and the volume is no exception. In order to cut down on time spent calculating Aurelion Sol's volume, we'll be approximating his body shape and dimensions. When Aurelion Sol flies in a single direction for a little while, he starts to stretch out his body, making more of a defined shape than before. One might also notice that his head is the largest part of his body, which begins to taper off towards his tail. Using his limbs as a little extra volume in these areas, we can approximate a cone for the shape of Aurelion Sol's outstretched body. First, we must approximate the height of the cone, or the length of Aurelion Sol's body, which appears to be just shy of a star's orbital diameter, about 95%, which comes out to be about 5.191 meters. Second, we must find the radius of the cone, and in order to do so, we can use the same ratio method that we did with the Moo. At the base, Aurelion Sol's length to width ratio is about 6 1/3 to 1, meaning that he has a width of 0.820 meters and a radius of 0.410 meters. Now, all we have to do is plug in the numbers to the formula for the volume of a cone, v equals 1/3 base times height, where the base is 2 pi r. That gives us a final volume of 0.914 cubic meters. Lastly, we just need to use a simple formula of density equals mass over volume to get a final density of 4.891 times 10 to the 11 kilograms over meters cubed. That puts Aurelion Sol high up on the scale, but not the highest in terms of density. At the bottom of the scale are red giants with densities averaging about 0.1 kilograms over meters cubed. At the other end, we get neutron stars with incredible densities of up to 1 times 10 to the 19 kilograms per meters cubed. That's a 1 followed by 19 zeros. More familiar stars, such as our medium-sized Sun, have average densities around 1,000 kilograms per meters cubed. If we move way up on the scale to white dwarfs, we start to get pretty close to Aurelion Sol. White dwarfs average a density of 1 times 10 to the 9th kilograms per meters cubed, or 1 billion kilograms per meters cubed. This puts Aurelion Sol only about 100 times more dense than the average white dwarf, which, in the case of stars, is not that much. So, to finally answer the question, what type of star dragon is Aurelion Sol? He's a white dwarf. Just a bit more dense. Before the video ends, I wanted to say thank you for watching, and I want to announce the new channel I'm creating called Hextech Physics. Each video will be based around a single champion's ability, and I will dissect that ability, answering one major question revolving around it. Additionally, if you're interested, I have another channel where I make videos about my friends and I playing League and just having fun. So, if that seems to interest you, I would love for you to check it out. Anyways, thanks for watching, and I'll be back with another video soon.